I want to finish off this problem with the Canadian nuclear reactor and then finish the other problem as well, so we'll have both of these together. One of the expressions that I developed in class today was for the final velocity of one of the particles when you have an elastic collision. And the expression that I ended up with looked like this. It was V1 final is going to equal M1 minus M2 times V1 initial plus 2 M2 V2 initial divided by M1 plus M2. And we're going to be able to use this expression here. We're looking at a special case where if this is object 2, for instance, this could be object 1 and this is object 2. Object 2 is initially at rest, and object 1 is the thing, the fast-moving neutron that we want to get rid of the energy of and slow it down quite a bit. Well, if V2 initial is 0, then this expression simplifies to V1 final will equal M1 minus M2 divided by M1 plus M2 times V1 initial. And so it's just going to be a simple fraction of what the initial velocity was. Well, in this case, we have the incoming neutron that has a mass of 1.0 atomic mass units. That's what the U stands for. And then it hits the deuteron that has a mass of 2.0 atomic mass units. And so these are M1 and M2. And what we'll get for the final speed of the neutron as a fraction of its initial speed is just going to be V1 final is going to equal M1 1.0 U minus M2, which is 2.0 atomic mass units, divided by the sum of those two. Well, 1 and 2 is 3, so 3.0 U times V1 initial. And what we find is not just the magnitude of the speed, but also the direction. This will be negative 1 over 3. It's just going to be minus 1/3 V1 initial. And so the incoming neutron will recoil from the deuteron and have 1/3 of its initial speed, heading in the opposite direction. So that's what's going to happen. Now, what about its kinetic energy expressed as a fraction of its initial kinetic energy? Well, this would be, whoops, let's try this again, 1/2 M1 V1 final squared divided by 1/2 M1 V1 initial squared. But everything divides out. V1 final is 1/3 V1 initial, so, and that gets squared, and what we end up with is its kinetic energy is dropped to 1/9 of its initial value. Now, how many successive collisions will reduce the speed of a neutron to 1/59,000th of its original value? Okay, now they're just asking about the speed, dropping it down to 1/59,000th of its original value. Its kinetic energy would end up being 1 over 59,000 squared, which is going to be a very tiny fraction of the original value. But if we're just thinking about reducing the speed, we reduce the speed by 1/3 every time there's a collision. And so we're wondering, how many times do you have to do that to get 1 over 59,000? Well, this looks like maybe you could take a logarithm of both sides here, and you'd have, actually, if I do a little bit of work with the equation here, so that I have 1 to the n on top over 3 to the n on the bottom, and that'll equal 1 over 59,000. What I actually have here, 1 to the n is just 1, doesn't matter how many times you multiply it together, but I'll end up having 1 over 3 to the n equals 1 over 59,000. If two fractions are equal, so are their reciprocals, and so I'm testing the idea of what value of n stuck on a 3 as an exponent will equal 59,000. We'll take a logarithm of both sides, and you'll get n times the log of 3 is going to equal the log of 59,000. And you could do the same thing with natural logs or anything that you like. But anyway, n is going to equal the log of 59,000 divided by the log of 3. And so plug in the numbers on that, and I get about 10. Okay. So after 10 collisions, the speed of the neutron is going to be down to 1/59,000th of its original value. So that's all it takes to figure out that problem. And we did use this expression that we developed in class and found out that V2 initial is 0, that it simplifies quite a bit. And this also tells you anytime you have an object, a mass m1, that's bouncing off of an object m2 that's at rest, if the mass of m2 is greater than the mass of m1, it's going to recoil in the opposite direction. Now again, this is an elastic collision, one in which the total energy, kinetic energy, is conserved. So that's a special kind. Let's take a look at something that's not a collision but a breakup. We have a neutron at rest decaying into a proton and an electron, and by now you know that a neutron doesn't just decay into a proton and an electron. There's also a neutrino that comes out of there, but energy is released in the decay, and it appears as the kinetic energy of the proton and electron. And the mass of the proton is 1,836 times the mass of an electron. What fraction of the total energy released goes into the kinetic energy of the proton? Well, here's the situation. We start off with a neutron that's at rest here, just sitting there, and what happens is it breaks up into a proton and an electron, and the electron takes off out of here with V sub e. The proton heads in the opposite direction with a V sub p, and conservation of momentum tells us that the mass of the proton times its velocity plus the mass of the electron times its velocity is going to equal 0. There was no momentum to start with. In a closed system, there can be no momentum afterwards as well. Now, if you've got two things adding together to be 0, they must be of opposite sign, and that's because the proton recoils in one direction and the electron recoils in the other. And we can figure out what the velocity of the proton is compared to that of the electron. Mass of the proton is going to be equal minus m sub e v sub e. Well, the mass of the proton is 836 times the mass of the electron, so this is 1836 mass of the electron times Vp is going to be minus the mass of the electron times Vp. And what you find out is that the velocity of the proton is opposite that of the electron, but it's 1/836th of the velocity of the electron. Or speed-wise, you could say that proton's speed is 1/1836th the speed of the electron. Now, what about the fraction of the total kinetic energy released? Well, here's the kinetic energy that's released. It'll be 1/2 the mass of the proton times the velocity of the proton squared plus 1/2 the mass of the electron times actually it's the speed squared, the speed of the electron squared. That's Ke total. Well, the kinetic energy of the proton, Ke proton, is just going to be the 1/2 m sub p v sub p squared. So we want to know what fraction this is of the total. In other words, what we want to know is the kinetic energy of the proton divided by the kinetic energy total. Well, we've got expressions here, and we can simplify these. So we'll have 1/2 the mass of the proton, velocity of the proton squared, over that total stuff there. Okay, I've got a 1/2 in every term, so I can knock those out. Don't have to worry about them. Let's see, we know that the velocity of the proton is going to be 1/1836 that of the electron, and the mass of the proton is 1836 mass of the electron. So I'm just going to call this capital F for fraction. Okay, so starting up here, that fraction is going to equal, everywhere I see a mass of the proton, I'm going to replace it with 1836 the mass of the electron. So I'll have 1836 mass of the electron times the velocity of the proton squared divided by, again, 1836 mass of the electron, velocity of the proton squared, plus the mass of the electron, velocity of the electron squared. And before, I found out that the velocity of the proton is 1/1836 the velocity of the electron. So if I make that substitution, well, for one thing, I can see that I've got mass of the electron in every term, and so that'll simplify things. So my fraction is reduced to 1836 velocity of the proton squared over 1836 velocity of the proton squared plus velocity of the electron squared. And then I can make this substitution for the velocities of the protons, and I'll have my fraction is going to equal 1836 times 1/1836 times the velocity of the electron, and the velocity of the proton gets squared, so this will be squared, divided by this same thing on the bottom, 1836 times 1/1836 velocity of the electron squared plus the velocity of the electron squared. And this will end up being, when you square this, I'd have 1836 squared on the bottom, but I've got an 1836 on top, so I'll actually end up with the fraction equaling 1/1836 the velocity of the electron squared. That's the top. On the bottom, I'll have that again to start with, 1/1836 velocity of the electron squared plus the velocity of the electron squared. And This simplifies quite a bit more because every term has a velocity of the electron squared in it. I get 1 over 1836 on top, 1 over 1836 on the bottom, plus 1, which is actually 1836 over 1836. And that fraction is going to simplify to, let's see what we get. I'll have 1837 over 1836 on the bottom. Flip that and multiply. And I'll have, let's see, well, I better do it in steps, because I can't entertain that much. I end up with 1 over 1837 is what I end up with. That's the fraction of the kinetic energy released that goes into the proton. So the electron ends up with the other 1800, well, it ends up with 1 minus that, which ends up being 1836 over 1837. Almost all of the kinetic energy goes into the electron, and the proton ends up with very little of it. So that's the fraction of the total energy that the proton ends up with. Okay, a couple of kind of interesting and fun problems for conservation of momentum.